Let us continue our discussion about number system. So let's discuss first what is binary representation. So basically, in digital system, all data, all input will be transformed into binary, into two states, because binary is the language of our digital system. It is the only representation that can be understood by our digital system. So what is binary? It means two status. So for example, we have 1, 0, true, false, hot, cold, on and off. But in reality, we don't only have two data in a set. We have more than two. So for example, in an integer, we could have lots of numbers, or in an answer in a question, we could have multiple answers, or in temperature, is aside from hot, cold, we could have lukewarm, cold, and other temperature. And how about the status of our faucet? It's not just on and off, but we could include leaky. Okay, so if it's more than two, how we're going to represent those data if binary is only two status. So the theory behind it, the concept behind how we're going to represent more than two data in a set will be discussed in data encoding. Okay, so in this video lecture, we're going to focus on the number system used in digital system. Okay, so that's binary representation. Again, representation of data in digital system. Now let's move on with number system. So number system is a manner how we represent, how we express our numbers. Okay, how we express how big the number is, how small the number is, what is the weight of the number, or how small it is. Okay, so how do we determine, how do we differentiate one digit to another digit? So it is based on these three parameters, the digit itself. Because in number system, in every number system, we have different digit that we use to represent a specific value. So for example, in decimal, we have 0 to 9. So the highest value is 9, the lowest value is 0. And also, we could have multiple digits in a number. We could have 3 digits, 4 digits, 5 digits. And each position on those digits, on that number rather, okay, will define how big the digit is. So for example, in decimal, we have 1, 0, or 10. So 1 positional value is 1/10. How about 0? It's ones. We all know that tens is bigger than ones. Even though they have the same number, same digit, if it belongs to different position, it means they have different weight. Okay? And the third is the base of the number system. So related to positional value, so it defines how big each position is. So for example, in decimal, so each position is based on 10 levels, 0 to 9 for each level. Okay, and another way of representing, or another word refers to base is radix. If say radix, it's the base of the number system. Okay, the weight of each position. We call it radix, okay, or base. And to determine what is the base of the number, of the given number, we use this notation. Okay, we use subscript. So if it's n subscript 2, it means base 2. If it's subscript 3, it means base 3. Okay, just to differentiate one number system to another number system, we use subscript. Okay, and in case there's no subscripts, automatically it is decimal since it is our language. Okay, so again, no subscript means automatically it's decimal. Okay, don't forget that. So we have four number system used in digital system. Four basic. So we have base 2, base 8, base 16, and base 10. So again, base 2 binary. So we have two status 0 and 1. And each digit in binary, we call it bit. And again, binary is the language of digital system. Every data will be transformed to binary. While base 8, another term, octal. So from 0 to 7. Okay. And it is used for short notation of binary. Okay. Later, you're going to determine why is it considered a short notation of binary. Okay. So it will be discussed when we when we discuss the conversion. Okay. So how about base 16? So another term, hexadecimal. So base 16 means we're going to use 16 characters to represent our levels in one position. Since decimal only have 10 characters, so it means in base 16 we're going to use letters to represent that the values that exceeds 9. So A 10, B 11, C 12, D 13, E 14, F 15. And again, 1, 0, or 10 is for one position in hexadecimal. If we are referring 1, 0, two decimal places, two positional places rather, it is different from A. Okay? 1, 0 of A is intended for one position. And if we're referring to 1, 0, two position, they are different. Okay? Don't forget that. And base 10, decimal 0 to 9, definitely is for human. Okay? So to differentiate each number system, okay, we could differentiate it through its positional notation. So based on our previous discussion, based on the previous slide, in decimal, each position is based on 10. Okay? So we multiply a certain 10 to get to this position, same as with 4, 5, and 7. Okay? So how do we get 1,457? By adding 1,450 and 7. And how do we get 1,000 based on 10? So we multiply 1,000. Since 1,000 is multiple of 10, divisible by 10 rather. Okay? So we could rewrite it as 1 times 1,000. For 400, we could rewrite it as 4 times 100 since 100 is divisible by 10. And 5 times 10, definitely divisible by 10. And 7 times 1, okay? So 10 raised to 0. So when we rewrite 1,000 based on base 10, so we have 10 raised to 3, 10 raised to 2, 10 raised to 1, 10 raised to 0. So therefore, 7 has this positional value, 5, this is the positional value, and 10 squared for 4, and 10 cubed for 1. Okay, so as you can see here, from right to left, the exponent increases. Therefore, when you go from right to left, the digit is bigger compared with the right digit. Okay, same as with octal. The only difference is the weight of each position. Now it's 8. The first position on the right side, which is 5, has a positional value 8 raised to 0, while for 1, it will be 8 raised to 1, 2, 8 raised to 2. Again, from right to left, it increases by 1. For hexadecimal, 1056. 6, first digit, will have a positional value 16 raised to 0, 5, 16 raised to 1, 0, 16 squared, and 1, 16 cubed. While for binary, so we have 1, 1, 0, 0. So the positional value for the first 0 is 2 raised to 0, 0, 2 raised to 1, 1, 2 raised to 2, and the last leftmost one will have a positional value of 2 raised to 3. Okay? So definitely 2 raised to 3 compared with 16 cubed, 2 raised to cube is smaller. Okay? And this is just a summary of um, comparison between decimal and binary based on the positional value. Okay, so we have positive here, and in case if it's negative, the exponent is negative, it means it is fraction. Okay, it's after, if we were talking about decimal, it's on the right side of the decimal point, the fraction part. Okay, so it will have a negative exponent. So -1, -2, -3, -4, -5. So the equivalent of -1 is 0.1, -2, 0.01, -3, 0.001, and so forth and so on. Same as with 2. So again, exponent, negative exponent means we are referring to fraction. Okay, so 2 raised to -1 is 0.5, 2 raised to negative is 0.25, and so forth and so on. Okay, and based on this, same position, same exponent but different radix will have a different result. Okay, so and also in binary we use prefixes to determine how big our our data is, or how big the binary number is. So if you're going to use kilo, so it means 2 raised to 10. If it's mega or M, it means 2 raised to 20. If it's giga or G, it means 2 raised to 30. And tera is 2 raised to 40. Okay, so we use this notation as prefix to our binary digits. Okay, so that's it for the number system. Okay, again, we have binary, octal, hexa, and decimal. They differ based on on their radix, on the weight of each digit, on the number of characters used. Okay, so that's number system. So in our next video lecture, we're going to discuss conversion of number system. How do you convert from binary to decimal, decimal to hexa, and so forth and so on. Okay, so see you in the next video lecture. Thank you for listening.